Alright students, we're going to continue this lesson on transformations of a graph, and now we're going to go into reflections. We've already talked about vertical stretching and shrinking. We've talked about translations, meaning sliding left and right, up and down. Well, now we're going to reflect, and there's two types of reflections that we're going to discuss in this section, and that is a reflection over the x-axis. Well, actually, we'll do the y-axis first. And then a reflection over the x-axis. Okay, so two reflections, one over the x-axis and one over the y-axis. So let's get a vision of what it looks like to begin in reflecting over a y-axis. If we have a graph, and we have, suppose we have something like the square root function that looks something like this. And we're just going to make up points. Suppose we're going through the point 4, 2, and also through the point 9, 3. Now if we want to reflect this over the y-axis, the other graph would look something like what I just kind of, the little dashed line I'm trying to make here. The reflection would look something like this dashed line. So in other words, the point 4, 2 would reflect over to the point negative 4, 2. And the point 9, 3 would reflect over and become the point negative 9, 3 over in quadrant 2. So when you reflect over the y-axis, you can see a pattern here in these ordered pairs, in that when a point, suppose there's another point further out, we'll just call it xy. If it's reflected over the y-axis, it would become negative xy. So the y values stay the same, but the x values change sign from positive to negative when you reflect from quadrant 1 over into quadrant 2. So in other words, your points xy become negative xy when you reflect over the y-axis. Over the y-axis. So for instance now, if you have an example such as y equaling the square root of x, and you want to rewrite this equation reflected over the y-axis, then the y remains the same, but the x becomes negative x. Now you can put this in your calculator, both of these, and when you graph them, you'll see that the line on the right is y equaling the square root of x, but the graph on the left, which is dashed here and not very good, but it would be y equaling the square root of a negative x. So be sure you go ahead and verify that on your calculator. Now we can also reflect over the x-axis. Let's look at the same graph, but this time let's reflect it over the x-axis. So let's suppose this is the point 4, 2, and this is the point 9, 3. Now if you come over the x-axis, it would look something like the dashed line. The point 4, 2 would then become 4, negative 2. And the point 9, 3, when reflected down, would become the point 9, negative 3. So the pattern would be a point xy reflected over the x-axis would come down to become x, negative y. So x, y reflected over the x-axis will become x, negative y. So if my original equation was y equaling the square root of x, and I want to reflect it over the x-axis, then this time the x remains x, but the y is replaced by negative y. Now it's kind of uncommon to have the negative on the left side, so if we were to divide both sides of this equation by -1, so it just says y equals, then it would say y equaling negative in front of the square root of x, and that would be your reflection. So in other words, this top line would be y equaling the square root of x, and the reflection down here would be y equaling negative the square root of x. So when we reflect over the x-axis, you'll see a negative in the front of your equation. Almost, if the negative is on the number which is giving a vertical stretch or compression, then that's going to give you the reflection over the x-axis. So let's take a look at a couple of these examples. So we have y equaling the square root of x, and they asked me to reflect it over the x-axis. Then y would be replaced by -y, and then if I divide each side by -1, it's the negative square root of x. The same thing with the absolute value of x. If I reflect over the x-axis, then I would take y and replace it with -y, and then divide both sides of the equation by -1, and the reflection would be y equaling negative absolute value of x. Graphically, this would be the V shape of y equaling the absolute value of x, and if it was reflected over the x-axis, it would look like this, and it would be y equaling the negative absolute value of x. Now let's look at some combined examples. Okay, so if we start with this, f of x equaling -2, x minus 1 squared plus 3, then what we know is the parent function is y equaling x squared. This -1, which is grouped with the x value, is going to be horizontal movement, and so it is not left 1, it is right 1. Then the 2 in the front, this 2, a number bigger than 1, is a vertical stretch. Then the negative in front of the 2 is your reflection. That, like I said, that negative in the front will cause a reflection over the x-axis. And the +3 on the end is going to be up 3. Okay, let me see if I can just sort of sketch this. So y equaling x squared would be a U shape. And again, this is not to scale, I'm just sketching it. The -1 is going to take it to the right 1 unit here. So the origin is moving to the right 1, placing it in this location. Then the 2 gives it a vertical stretch. So narrow it up, give it a vertical stretch, narrow this thing up, and make it more narrow. Now, the narrow version is going to be reflected down. So it's going to look like this when it's reflected down over the x-axis. And then the last thing I do is take that reflected version up 3 units. So 1, 2, 3 right here. In blue, it would look something like this graph in blue. Okay. Now, the new vertex would be the fact it went to the right 1 and up 3, would have a vertex of 1, 3. Okay, let's try this one. Our parent function would be y equaling the square root of x. Maybe I should put it over here. That would be our parent function. That's our start. Then we would come in here. The +3 is grouped with x. So So it's not right 3, it's opposite. It's going to be left 3. The negative in the front, now there's no vertical stretching or shrinking here. That negative is going to tell you to reflect it over the x-axis. The -5, the number on the outside end, is going to tell you up or down, and this one will be down 5 units. So if I sketch something that looks like y equaling the square root of x, then I take it left 1, 2, 3 units, be over here. Then I reflect it over the x-axis. We'll place it under the x-axis down here. There's my reflection. And then down 5 units, my final graph. Take this point down 1, 2, 3, 4, 5 units. And this will be a sketch of your final graph. Takes a little practice. I erased up here real quickly working on how my parent function is y equals x. Okay, so in blue is the final graph. And here's another one. Okay, this is like a double negative in here, so we've got to be pretty good at this one. Alright, so my parent function is y equaling the square root of x. The first thing happening is the negative on the x. So if you replace x with negative x, and we don't do this one very much, but if you replace x with negative x, which is what has happened here, then this is a reflection over the y-axis. X replaced with negative x would place it like from quadrant 1 over to quadrant 2, which means you're coming over the y-axis. Then the negative in the front is another reflection, and this is the reflection over the x-axis. Last but not least, the +1 on the end would be up 1. Let's see if we can do this. Okay, so here's the square root of x. I'm going to reflect it first over the y-axis, which puts it over here. Then I'm going to reflect it over the x-axis, which puts it down here in quadrant 3. Then up 1 unit, my last graph I'm going to put in blue, up 1 unit. This should be my final graph in blue. My final graph is in blue. Okay, now we have this unusual function. We're through doing all of our transformations. And now we have this unusual function called the greatest integer function. So before we talk about a greatest integer function, I need to remind you what an integer is. An integer, those are numbers which we normally put on a number line. Okay, these are the numbers we normally put on a number line. Now, an integer is not, an integer, something that's not an integer is a fraction like a half or a third or 3/4 or a decimal like 0.7 or 0.25. Anything that is not a perfect number, like a perfect whole number or it's negative. Integers are whole numbers and their negatives and 0. Okay, those are your integers. So the greatest integer function, let me just go ahead and create a table here. Maybe this will help. The integers on this table would be like -3, -2, +2, and +3. And all the numbers in between there are integers also. Those are your integers. But the things that are not integers are the numbers like -2.5. That's not an integer. Or -1. Hold on, that is an integer. -1.5 is not an integer. So when you put the decimals or you put fractions, like maybe you put 7/3, that is not an integer. Okay? Those are your numbers which are and are not integers. Now, when I try to graph this in a greatest integer function, your x values do not have to be integers, but your y values must be integers. So, If my x value is an integer, then my y value will also be that integer. But if my x value is not an integer, my y value has to be an integer less than the half or bigger than it. So when x is 1/2, y is either 0 or 1. And when you go down to the lower number. So if I put 2/3, my y value has to be an integer, either 0 or 1, but I go down until my x value changes to an integer, and then my y value will be that integer. So if I go a little further and I say 1.3, the y value has to either be the integer 1 or 2, and it goes down to the 1. Or if I put 1.7, the y value has to be an integer, either 1 or 2, and you go down to the 1 until you go to an integer itself for x, and then the y value is that integer. And you take it a little further. If I put 2 and 2/3, the y value has to be an integer. It's going to either be 2 or 3. It goes down to 2 until I change to 3, and then the y value is the 3. So the x values are real numbers, but the y values are integers. Now, when you graph this, they call this the step function, because it turns out that you're solid on the left of every bar and you're hollow on the right. You're solid on the left, you're hollow on the right. Solid on the left and hollow on the right when you graph these values. So the point 1.71 is on this bar. 1.71, I'm having a hard time showing where I am. Let me try a different color. Maybe if I go orange. Okay. The point 1.71 is here on this bar, right? Because it's 1.7 for x and jumps 1 for y. And all of those decimals are going to be on the bars, and all of the end points are these combination points that are both integers. So it's a pretty interesting function. It takes a little while to learn how to do this. And this function, and it goes to the negative, it's so hard to do. Goes to the negative version over in quadrant 3 also. It continues. And this is just informally referred to as the step function. Okay? So the greatest integer function is also called the step function. Now the greatest integer function has this symbol on the x value like what I just drew. And I'm not sure why it didn't type in like that when I typed the notes, but that's what it really looks like. And sometimes you will see it as the int of x on some of the calculators, because that notation is a little bit hard to get on a calculator. Now the only other thing you're really going to see with the step function is they might ask you a question like this. What is f of 0.23? Well, the answer is an integer, because this is the x value in the parentheses. So in practice, the integers around 0.23 are either 0 or 1, and you would go down to the 0. One more example. If you had f of 2.78, the integers around 2.78 are 2 and 3, and you would go down to the 2. This would be your x value, and this would be your y. These ordered pairs would be 0.230 and 2.782. Okay, I believe that's finally the end of this section. Thank you for your patience, and I hope that it was explained well enough that you can understand it.